Here, Steve and Stefan in the same talk. I mean, I'll be the chairman of both of them in the same talk. It's a great honor for me. Even if I try to be the kindest person on earth, I wouldn't feel so kind and as them when I go to visit them in Concepción. So they're very good friends and good research collaborators of mine. So I have worked with Steve, as you know, in two different institutions. I visited in Concepción 2 times, and it's very good for me to be here with them. So this talk will be like half and half. So we'll have the first half of the talk given by Steve, and the other half given by Stefan. And we look forward to hear from them what they are doing in Concepción about next generation fiber optics. Thank you, Steve. Thank you, Stefan.
Okay, you can hear me? Okay, good. Hello, everyone. I hope everyone had a good lunch. Yes, so as Daniel said, this will be the second class of the Stefan and I. We will split the talk, so I think it's probably going to be Paraty first. Marcelo, this is the first time a course has been split during the, well, ever, right? But also during the time, right? So yeah, so we'll see how it goes. So we were talking the other day about these multi-core optical fibers which we have in Concepción. And so, yeah, so I'm Steve. Esteban is sitting right here. If you haven't met Esteban yet, you'll see him in, say, 37 minutes. Okay, so here's what we were talking about. What we talked about in class 1. We sort of introduced this type of multi-core fiber technology, and I told you about some of the devices we had and why we're interested in this and so on. And so now the second class, I want to tell you about some experiments which we can do with the multi-core fiber, and in particular, I think we both have chosen experiments which are really well suited to the multi-core fiber. So these are experiments that maybe would be much more difficult, or perhaps not even possible without this multi-core fiber characteristic, this multi-core characteristic of the optical fibers. And then class 3 will continue and talk about entanglement and things like that. So, well, before we get into class 2, just let me review quickly what we talked about in class 1. So, as I said, in the telecom industry, you have this need to use structured fibers. So, in our case, we're using this multi-core fiber, where you have different fiber cores within the same cladding structure. And this was these cores are basically completely independent. There's no crosstalk, and this is quite nice. And so we have, multiple, say, channels within the same structure. And so just like a general comment, like all the development, all these different types of technologies bring us these new tools for quantum information, for photonic quantum information. So the way we encoded then information like this is, so if we have different, say, for each core we associate a basis state for a single photon, let's say. So 0, 1, 2, and 3 in the case of a 4-core fiber. So 0 means that the photon is propagating here in core number 0, 1, or 2, or 3. Here's a photo from a fiber microscope of the fiber, so you can see, it really does look like that. And so the idea is we can, we're going to want to send kind of general quantum states through this fiber. Here we have the characteristic that is, would say, be a 4-dimensional quantum state. If you have fibers with more cores, you can have larger dimensions and so on. And kind of one nice characteristic that appears when you're going to the quantum case instead of just classical telecom is that you have more phase stability between the amplitudes, or say, the photon can be in one of the cores, and so the kind of coherence between the cores is a lot more stable because the cores are in the same cladding. So thermal fluctuations, mechanical, the cores sort of feel that in the same way. Not exactly the same way, but a lot more so than if you were using, say, 4 individual fibers, and that's a nice feature. I showed you some other devices, so we can couple light in and out of the multi-core fiber using these multiplexer devices, in which these single mode fibers are glued onto the face of the multi-core fiber. So coupling is now can be very efficient. Another device which we talked a lot about was this multi-core fiber beam splitter, in which a section of fiber is heated and stretched so that the cores become close together. Then you do have crosstalk. You want to have crosstalk. This means that light from one core can escape into the others. I showed you how we can characterize these devices using a type of optical tomography, and we obtain, for this 4-core fiber beam splitter, we obtain typical unitary estimates, or estimates of the unitary matrix, something like this, which has a really high fidelity with this real Hadamard matrix. So this is kind of a really cool device for us to work with. And so the basis of, say, a lot of experiments which we do, and which I'll tell you about in a minute, involves building a type of interferometer like this, where we can use one of the beam splitters here, this pink box. We can apply some phases, and think of this as a state preparation setup or stage. We can then apply some phases and use another beam splitter, and think of this as a measurement device. So we can say prepare quantum states like this one here on the left, and we can project in a basis of states defined by these here on the right. And this gives us access to a huge, say, volume of the Hilbert space available in this 4x4 system, because it allows us to prepare and measure states in 4 of the 5 mutually unbiased bases for dimension 4. So 1 through 4 we can prepare just by changing the phases in the interferometer. And this is really nice because you can automate this, computer controlled, and you can set up your experiment, go home, go have lunch, whatever, come back and analyze your data. So that's kind of the name of the game. I also mentioned the fact that there's one tool which is missing from the toolbox, a tool which we'd really like to have, which is a phase modulator that can actually modulate the phases of each core inside of the multi-core fiber, each core individually. This we do not have. So the way we deal with this for the time being is we have to take the light, the photon, out of the multi-core fiber into the single mode fibers with these demultiplexer device. Then we use single mode fiber phase modulators, and then we multiplex back into the multi-core fiber if we need to. But with this demultiplexer device, that makes this not such a big deal. The one issue is that, okay, now we're in single mode fibers, now we kind of lose this phase stability aspect, but in all of our experiments we have to stabilize the phase anyway, so it is what it is, let's say. So this is kind of what an experiment looks like. So we have everything built into these devices, and then we have electronics controlling, say, the preparation stage, electronics controlling the measurement stage. For a lot of the experiments, we use, say, a weak coherent state as the input, so this will be kind of like an approximation to a single photon state if you say don't have enough money to produce single photons on demand. And so during operation of this whole device, we do this active phase stabilization, which is controlled by the electronics all the time. And so because of the phase stabilization and the quality of these beam splitter devices, we can get really high quality interference, which is key because this has allowed us to do some experiments. Esteban will present one where you really need high quality interference in order to kind of observe what you want to observe. So I'll let him tell you about that. So this is what a typical experiment would look like. So here, this part where the blue is kind of constant, this is where the phase is stabilized, so it's maximizing the counts, the blue dots. And then when we're in this stabilized region, we will switch to a measurement stage for a fraction of a second, take some data, go back to the stabilization, check everything's okay, measure, and we'll be flip-flopping back and forth between stabilization of the interferometer and measurement, right? So as I mentioned, that's why you really want if you have some inherent stability, that's good because that means you can be measuring more often. You don't want to be stabilizing the whole time, you're not measuring, right? So you're not taking data. So this is kind of the name of the game, right? And that's what we presented last time. So now I'm going to go to part 2 and tell you about some experiments. So I'll try to tell you about 2. Hopefully there will be time. So the first experiment is going to have to do with indefinite causal order. So I'm going to start giving kind of just a brief and kind of very operational description or introduction to what this is. I want to mention that if you're interested in this, in 2017, Czesław Bruckner gave a really great course about this. I mean, he's one of the inventors and principal scientists developing this field. So I encourage you to look for his course online from 2017. So yes, this will be somewhat brief and very, say, like an experimentalist view of this subject. So as you know, when you draw these quantum circuits, time kind of flows from left to right, and so everything is, say, in like a fixed temporal order. You know, I apply one gate, then I apply another gate, and so on throughout the circuit, right? That's kind of how we do standard quantum computation, and that's how we imagine operations in, say, standard quantum mechanics. We have a quantum state, we might apply some operation A, then B, and we have some output state. We could kind of change the order, we could apply B, then A, and have the output state. But in quantum mechanics, you have something even more general than that. Because of superposition, I could take my state psi, I could route it through operation A, route it through operation B, like following this yellow solid path, or I could route it first through operation B, then through operation A, right? Coherent, so it's, this would be a superposition of AB or BA, right? And the device that kind of allows me to do this in a coherent way is called a quantum switch, which I think many of you, I'm sure, have heard about. So this is kind of the name of the game that we want to explore, is this coherent routing of quantum systems through different operations. And so in order to do this, you need at least two physical systems, right? You need your initial, say, target system, your state psi, that A and B are your, say, gates that are going to operate on the state side. But then you also need a control system, which is going to represent the fact that now you have multiple paths here in your circuit. So this control system is going to decide this, and the dimension of your control system is going to be at least as large as the number of paths that you want to have right here. So here I need at least a qubit in order to realize at least a control qubit to realize this indefinite order of these two gates. So so this is something you can do, and it's been done experimentally for a little while now. So this is, I think, the first experiment that did this. So here, here's what their experiment looked like, the quantum switch part. So here down below they have the input side. It's entering into this experiment here from below. They have these unitaries here, which are wave plates. So this is going to be a polarization unitary 1 and a polarization unitary 2. So they want to go through, they want to do 1, 2, or 2, 1. So the way they do that is they have these beam splitters, which the first beam splitter will create a superposition of paths, right? So a photon with a given polarization state will come in here and either split to the right or go straight. They then route the photon either kind of this way through the device, so it kind of goes A, then B, and up to the second beam splitter, or the other path goes first through B, then through A, following that path which is on the right there. And then, so the two paths are made to meet on a beam splitter here, and then you have interference between these two possible processes, right? So if you do the calculation here, it's quite easy to do, but you can see that if you look at output port 0, which is the top one here, you should have something like proportional AB plus BA applied to the target state psi. If you have output port 1, your state is output port 1, you should have something like the AB minus BA applied to the state psi. And so, if you think, okay, well, that's cool, what can I do with that? Well, you can recognize that, well, this output port 0 will be equal to 0 if A and B are operators that anti-commute, or output port 1 would be equal to 0, or in other words, I would never see the photon in output port 1 if A and B operators are commute, right? So this is a way to test if I know that A and B either commute or anti-commute, this is a way that I can discover that, right? And I can discover that using each unitary operation only once, because the photon goes through A, B, or BA in superposition, so it's only going through each one of them once, right? So this allows me to kind of answer this question. So if you want to play a game and discover if they commute or anti-commute, you can build this device. and do it using only each unitary only once. So, okay, this is kind of cute and everything, it's nice, and so the question is, well, is this kind of thing useful? And so I'm going to show you, yes, I mean, there's a lot of work that's been done on this. So here's 2 papers where you can define, say, different, say, toy computational problems and show how this indefinite order is a resource in solving them more efficiently. You can do different problems in, say, communication complexity, and you can show that this indefinite order can help you there. What is this? Oh, okay, so you can see that if these A and B, instead of unitary gates, if they're, say, noise processes, you can show that putting them in indefinite causal order, you can actually increase the rate compared to going through them sequentially in a fixed order. And then another really cool paper that came out, I guess, 1 year ago, slightly more than a year ago, is that they showed how you can use this quantum switch to actually do time reversal of an unknown unitary process. I mean, I know I have a unitary process. If I know what the unitary is, I can undo it. But if I don't know what it is, I can't really undo it. But with the quantum switch, you can. So that's some cool, work that has also experiments associated. There's also a lot of internursing physics that people are looking at for this type of indefinite causal order and quantum switch device. So there's this process matrix formalism which was developed to describe this all in a consistent way, which Chaslov and others have developed. And so this is what he talked about in 2017 quite a bit. People are looking at this in terms of quantum gravity and closed time-like curves. These things I know nothing about, so I put them here in case it sparks your interest. You might want to go check out the literature. So in terms of experiments, there's this one done in Vienna, which I showed you already. There was another experiment a few years later in Brisbane, Australia. Again, looking at this, did they commute or not commute problem, and also calculating, say, weaknesses of indefinite causal order. This computational complexity advantage was also studied experimentally, as well as this idea of communication rates through noisy channels. So a lot of the main theoretical ideas have been tested experimentally. I just want to call attention, so all these experiments have been done for only 2 operations, right? 2 gates or 2 processes. But of course, you can take this idea to more gates, right? So I could imagine something like this, where, just for the sake of simplicity, let's suppose I have some unitary operators, n of them, and I want to go through in a different order, so I can go through kind of numerical order, or I could invent some other order through them, or whatever. So there's, if you stop and think for a second, well, there's n factorial possible permutations or possible orders that I could choose here, right? Entering in one and going through the rest, and there's n factorial total choices I have, right? So, okay, this is cool, and in fact, some of the applications I showed you are valid for this arbitrary n, right? So, for example, one of these computational problems, which was developed early by Mateus Araújo, who's also Paraty alumni, Fabio Costa and Chaslov Bruckner, who I already mentioned, they kind of developed this idea of this promise problem. And so, what is this? So the promise is that, so imagine I put these unitaries on a sequence, right? And I can define, say, a permutation of the sequence, pi x, as being equal to some number, just in a second, times the original sequence, the numerical sequence. So pi 0 is when I go through 1, 2, and so on up to n. Pi x is some permutation of these guys. And the promise is that this permutation satisfies this equation here, right? So x can take on n factorial different values, right? Omega here is a root of unity, right? And y here is some other number that can take on n factorial different values. And so this is the promise. These unitaries I have a set of unitaries that are such that this is true. And so the problem is, well, okay, find the value of y, right? So for a given y, this whole set of pi x permutations is going to have some relation here, right? And so I want to know what it is. And so, okay, let's just look at a really simple example. For n equal to 2, there's only 2 permutations, right? The original one, and then I switch 1 and 2, the order of 1 and 2, and in this case, omega is equal to e to the I pi, so the factor out here in front is minus 1 now to the y power, because here x would be equal to 1, right? Pi x equal 1 gives me this. So, of course, if you look at this for a second, I hope that you're all noticing that, well, this is exactly what we saw already. Basically, discovering the value of y here is discovering whether u1, u2 is equal to u2, u1, or equal to minus u2, u1. So finding out whether they commute or anti-commute. Okay. Yeah. So. Okay. So with the quantum switch, which we saw before, we answered this question as to whether they commute or anti-commute in, say, a single shot. In principle, we could find that once with a single use of the gates, and say there were 2 gate queries. So you apply u1 one time and u2 one time. So what happens when we try to do this in a fixed way? Yeah.
Sorry, but in your formula, you say that pi x will be omega to the power xy, then pi 0, right? So when you write the formula for pi 1, you say this, it should be omega, which you solve for.
This scenario. Thank you for, that should be the way. Sorry. Okay, so the quantum switch, we have to use each unitary once, so 2 queries, if you will, in total. If I were to try to do this with like a quantum circuit model, you need to use 3 calls to unitaries. So one way you could do this is I could have my control qubit, I could have my target qubit, and I could just say, always apply U2, but then I'll apply U1 before U2 if the control qubit is in the 0 state. That's what this open circle control means. Or if the control qubit is in the 1 state, I'll apply U1 afterwards. So if you think about it for a second, you see that this circuit will implement this. If I put the control qubit in a superposition of 0 plus 1, I can calculate these types of things, but I need to call unitaries, 3 queries to be unitaries. So in this sense, just in a simple example, you see this computational advantage because I made less queries to the unitaries. So this is the Araújo-Costa-Bruckner algorithm, or promise problem for dimension 2. You can, of course, go to larger dimension. They've designed it for larger dimension. So this, and in fact, a quantum switch, this type of idea with these n unitaries, is able to solve it, right? And it can solve it with only n queries. So the quantum switch is linear in the number of gate queries, whereas the fixed order is quadratic. So that corresponds to a quadratic advantage that the quantum switch has over any fixed order quantum circuit. So this is pretty cool. It's like, say a toy computational task that you can do, and you can try to use this as inspiration to find different things that a quantum switch could do, or versus a standard circuit. The problem, say, from an experimental point of view with this algorithm, is that the target system which you use, which must have a dimension that is a multiple of n factorial. And so you can prove this. I won't prove it right here. It's quite easy. But the point is that you need a target system that's at least n factorial in size, right? So if you have n equal to 2, this is okay. You can use the polarization as your target system, like the previous experiment did. However, if you want to go to, say, 3 unitaries, you need a target system already at dimension 6, and so on. So it scales really unfavorably when you try to scale up to look at, say, more complex quantum switches. So now I'm going to go back to the multi-core fibers and tell you about an experiment which we did a couple years ago, where we were able to do this actually with n, or let's say we'll have 4 unitary. So we're able to scale this up using this multi-core fiber technology. So this is the paper that we published. I show it here explicitly because I think, at least 7 of the 12 authors here have been to Paraty, at least once, many of them multiple times. So you have Leandro Lita, who gave a course here at least once and was a student here in 2007 at least, in many of the years. Myself, Esteban, Gustavo Lima has been here at least once or twice. Marcio has been here as a student and then participated in the workshop and so on. So Mateus Araújo, who I also mentioned earlier, he was also a student here and has been back many times. So, okay, so going back to this Araújo Costa Bruckner problem for a second. So the way you would do this experimentally is you need to have this target system that's a large dimension, as I mentioned, but also you need to have, so these beam splitters, which before were just regular 2x2 beam splitters, you would have beam splitters that would have an associated unitary matrix, that would be described by a Fourier transform. And this is because these, if you recognize, these omegas here are exactly the elements of a Fourier matrix in a certain dimension. So that was sort of the kind of an inspiration point. As we mentioned before.
Sorry, could you elaborate on this point? What exactly is the Fourier transform matrix here?
Yeah, I guess I could. I can write here, right? Yeah. I guess I'm the first one. It's been a while. Yeah, so a Fourier. So, I mean, the best thing is I can give you some examples. That's probably the easiest way to do it. So, in dimension, so basically, these matrices are set up like this. You would have different powers of omega in the. So, if I have, say, different rows x and columns y, I have omega to the xy. So, in some random one, here would be omega xy. So, here I have omega to the 0 times 0 power. Here, omega 0 times 1, and so on, right? And here, the same, omega to the 1, 0, 2, 0, and so on, right? So that means that you have these matrices that look something like this. So they're always real bordered like this, right? So for dimension 2, you would have, here I have omega to the 0, so it's always 1. Here, also, omega to the 0, 0 times 1 is 0, is always 1. Here also is 1, and then here I have omega to the 1, 1. So if I have dimension 2, so n equal to 2, which means that omega, am I writing large enough? I'm sorry, you can ask further. Would be something like 2pi over 2 is equal to ETI is equal to minus 1, right? So it would look like this. So this would be, say, the Fourier transform matrix in dimension 2, right? Which is I'm also, there's a normalization factor here, which would be, say, 1 over the square root of this dimension here. So here I have 1 over the square root. So you see that's exactly the Hadamard matrix, which we saw earlier in at least one of the courses. So this would be a Fourier transform matrix in dimension 2. When you go to larger dimensions, you're going to have different powers of omega in the matrix.
Then does it mean that with this apparatus that you can calculate Fourier transform?
No, well, yes, but no, I get, essentially, so I mean, if you have say I have a beam splitter, it gives me a Fourier transform. If I send, a state through it, what I have leaving the beam splitter would be the Fourier transform of that state, but where the information is encoded in the amplitudes of my quantum state, yeah.
But because like Fourier transform is a very big bottle, can be a very big bottleneck in computation.
Mm-hmm.
That is why if you can do it in the analog way, that can be super fast.
Yeah. So this it's a really good point. Yeah. So you can do this. Works in this is kind of a general thing in optics. In optics, I mean, there's many different optical elements which perform Fourier transforms. Like a lens, if you look at the focal distance of the lens, you see the Fourier transform of what came into the lens, right? The spatial distribution of light coming into the lens. You look at the focal point, you see the Fourier transform. So this is kind of the basic idea of optical computing. So there's, in say the 1970s roughly, there were a lot of ideas of how you could use, say, optical information processors to do exactly this. The Fourier transform came essentially for free. When light propagates from one place to another, it's doing the Fourier transform. Just like when you look at far field diffraction, you see the Fourier transform of the near field, right?
And then you can also do fractional Fourier transform with that. But my question then will be, what is the reason why we don't have those processors today?
I think because analog processors, the digital processors are so much easier to do error correction, all those sorts of things. Yeah. There are optical devices that calculate correlations or autocorrelators and things like this, which use exactly this idea, but it's mostly for scientific use, right? Like you want to calculate properties of laser beams and things like this, you have a device that uses kind of these types of transformations.
Okay, thanks a lot.
Yeah. So the Fourier. So the point is, the beams. If you want to solve this problem where you have these coefficients given by these omegas, you would need a Fourier matrix, which just goes kind of like this. And there are beam splitter devices that correspond to that, right? But as we talked about before, we want to use multi-core fibers. And we saw that ours is in the Fourier transform. It's a Hadamard matrix, right? Given by this, right? So of course, in dimension 4, if you see, I'm going to have some terms here that are not going to be equal to, this matrix typically is not full of plus and minus 1. So in dimension 4, you have elements that can be 1, minus 1, I, and minus I, right? So you distribute it in different ways, right? So it's a different matrix. So
Probably it helps if you connect with something that you said in the first class, that was about nuclear bias bases. The Fourier transform is a good example of a change of one base to another neutrally biased one.
Yeah, okay, so if I construct, so I say the rows or columns of this matrix are all orthogonal, and I can use them to define a basis, right? In dimension 4, the Fourier transform matrix has the same property. The rows or columns are also all orthogonal. I can use them to define a basis. It will be a different basis. It will be mutually unbiased to this one, right? In fact, in the slide I showed the mutually unbiased bases, some of those vectors are exactly the rows and columns of these two matrices. So it's a change of basis. And here for us it's non-trivial because this is what we have in the laboratory, right? I have this, right? And so so this is what I want to use in, say, my quantum switch experiment. Let's see, I have time. I'm almost, okay, I got to get moving. So basically the point here is that this difference, right, kind of inspired us to find a different kind of problem. Instead of trying to say, okay, how do we make a Fourier transform? We said, well, maybe we can make a Hadamard type promise problem. And that's exactly what we did. So essentially, you can define an exact similar type of problem, type of promise, but instead of having these roots of unity here, we just have the elements of the Hadamard matrix plus and minus 1. And so you change. So instead of making the experiment fit the problem, we make the problem fit the kind of experiment we do. And this is actually quite interesting because you still maintain this quadratic advantage, which we had before. But at the same time, we lift this requirement that the dimension of the target system be at least n factorial. Actually, all we need is an even dimension, so we can even have a dimension equal to 2, irregardless of the number of unitaries we have. So we kind of decouple these two parameters, which makes it much more friendly experimentally. So that was kind of the key point here. And so, so just this kind of, I just want to mention, so with that kind of idea, we also developed some other types of promise problems and there'll be a post next week by Jorge Escalon, who's also here this week. But so if you want to talk to him about that, please do. So this is the experiment we did, right? We used actually 4 unitaries, and we routed the photon through them in different ways using these multi-core fibers. So here's the different routings that we did. And so, of course, with this problem, we're not obliged to have n factorial different permutations. We can have, say, 4, which is what we did. And so this is what it looks like in the lab. Here, these, like right here, for example, is a liquid crystal rotator. So we control this electronically. We can turn it off and on, essentially. And then here's the multi-core fiber. So the light comes out from the multi-core fiber through here and then goes to another multi-core fiber. And then, so photons, for example, coming through here to start with A, then gets routed back around, comes through, say, B, gets routed back around, comes through C, and so on. So this is the kind of thing I want to show you this because this is really only possible with multi-core fiber. And if you have, these integrated chips and so on, you can't do this. In bulk optics, it's I would say, impossible, or at least much more cumbersome. So, in interest of time, I'll just go through this really quickly. So this is what the experiment looked like. We have, we basically build this interferometer, right? So you can see the same kind of feature here. That's my time, pretty much.
We are 10 late, so we still have more.
Yeah. I was starting from the moment I started, so yeah. Can I have 5-10 more minutes? Okay. Yeah. So so you see, here's the multi-core fiber beam splitter, here's the beam splitter, so this hole here is an interferometer, and inside the interferometer we put this switch, which I told you is this routing here that's done by the multi-core fiber. And so, there's so this is what it looked like in the lab, this is the what I just showed you, and then this is the whole thing. So this is kind of the interferometer. Again, all the fibers are here in this foam, which keeps them more stable. Here's the optical switch where the photons are being routed through these liquid crystals. And then if you've been in the lab and you know what these are polarization controllers. So there's actually 20 of them here in this experiment, and they have to be aligned perfectly in being. So this experiment took like 8 hours just to align the polarization, and then about 5 minutes to do the experiment because it's all automated, right? So it was like we would have to arrive early, working in shifts to get it all aligned, and then you would press go, and 30 seconds later, you had enough data to go home. It was kind of disappointing, so just to give you some details, because I think this is a really cool experiment. So the control system here is the spatial mode of the photon. The target system is the polarization. Again, these liquid crystals are here. So another really cool thing is we had, say, because these problems a lot of times are cast in terms of, say, an oracle. Like I send my photon to an oracle who's going to apply the quantum switch. This is kind of the way you cast these problems. So we actually have 2 different, say, electronic systems. One is the user, who is preparing the photon in the superposition state, and then you have the oracle who's applying the polarization rotations, right? So, and they are separate, right? And then we have a detection system looking at the counts. Another cool aspect is that, so the way it worked with the liquid crystals, we would have the multi-core fiber would be here, and so the light would say come from this fiber and then get mapped onto this one, passing through this liquid crystal rotator. And so, at the face of this fiber are these 4 little points. So there's a lens here, and so at say an image plane, you would see the 4 little points. But then we place the liquid crystal in the Fourier plane, where all the points come together and overlap. And that's interesting because with that, you guarantee that the unitary operation that's applied to light coming from each of the cores is the same. So this is what it looks like in the Fourier plane. You see basically an interference of 4 points, make this sort of pattern. And so that's kind of an interesting aspect, because one of the criticisms of early experiments was that, you went through the same wave plate, but you went through the same wave plate at different spatial points. How do you know that it's the same unitary, right? You can imagine something where I don't know what the operation is, so you want to be sure it's exactly the same for all paths. Okay, so so just experimental results. This is So I just want to show you these are the different types of unitaries we applied. Very simple Pauli operations and Hadamard operation. And so these are sort of the success probabilities. So we have pretty good probability. And here's some of the measurement results. So all this I pretty much mentioned. So just for the sake of completeness, so this is Marcin Thaler figured out, okay, how could you possibly implement this in a fixed order circuit model? And this is this one option. And so it's I think this is what the minimum number of unitaries possible, which was 9 calls for unitaries, along with a bunch of say controlled swap operations and Scylla qubits and stuff like that. So you can see that this higher order quantum switch you really start to see some of the advantage, right? Okay. Let's see. So I have to make a decision here in terms of time. Okay. I mean, can I have 5 more minutes? What? Yeah. Okay. I just want to really. So really quickly, I want to tell you about one other thing because I want to mention something to you here at the end. So another thing you can do with this beam splitter is to make a quantum random number generator, which the idea is really simple. You send a photon on the beam splitter, it gets split between the 4 paths, and then one of the detectors is going to click with a probability of something like 1/4, and then in principle you could have, say, up to two random bits produced by this device, right? If I send in a single photon. So this is a cool idea that's been around for a long time, more than 20, 25 years. But there's a problem, which is if I'm just looking at these detectors, how do I know that the clicks I'm seeing are due to the photon that came through the beam splitter? How do I know that someone's not, maliciously turning the detectors on and off and making them click or not click, producing seeming in a way that seems random to me, but is completely known by them, right? So if I'm using this randomness to make a lottery raffle, I don't want anyone controlling my random number generator. And in fact, this kind of thing is done, and hacks on this type of device have been shown using, say, light, external light to attack the detectors, and you can make them go blind or make them click on purpose and so on. So this is an issue because this type of device is, you have commercially available quantum random number generators. We want to protect them from this type of problem. So one experiment we did, and so we did a quantum random number generator in a more device-independent way. And so I don't think we've heard about device independence yet in this school, but so I'll just mention really quickly. In quantum physics, you can design protocols that allow you to, say, realize different tasks with even untrusted or uncharacterized equipment. Glauci talked about this a little bit this morning. But so kind of the flagship one is say device-independent QCD, where you can use, say, Bell's inequality to do this, so you can be sure that you have your statistics correspond to, say, non-classical correlations. You don't have to know really much of the underlying physics of your devices and so on. That doesn't enter into Bell's inequality anywhere. So this kind of idea has been around for, say, at least 20 years. More recently, you have this idea of semi-device independence, where, maybe violating, loophole-free Bell inequality violation is demanding. Maybe you can make some more, like 1 or 2 assumptions about your system, kind of justifiable assumptions, and you can have something that's known as semi-device independence. So I say weaker, but more realistic, more feasible, especially in the laboratory. And then you have something called measurement device independence, where you say, okay, well, suppose I have a state preparation device that I trust and totally characterize. It's perfect. I know exactly how it works. I could use that to realize an experiment where I don't trust the measurement device at all. And so that's what we do. And so there's other types of device independence, just to mention that. So this is the idea. We have this interferometer, which we described before, but now I'm going to consider that this whole section here is the state preparation, and then just the detectors on our measurement station. And so the idea is, okay, I want to treat these detectors now as a black box, completely uncharacterized, untrusted. This black box is going to output some events and clicks of photons. And now I will use a state preparation device to realize a quantum random number generator in a way that I don't have to, that I know that the clicks are coming from my states, right? And so the idea here is, well, I could prepare, say, instead of just sending a single photon blindly, I could prepare it in different ways. So I could, say, produce two different types of states. These four states would be, say, computational basis states, in which the photon is going to leave here in one of these black arrows, and then the other state could be the superposition state. And of course, the superposition state, when I prepare that, the output of the detector should be random, right, if everything's working properly. If I prepare one of these computational basis states, well then, if I prepare state J, I should expect detector J to click, right? And so in this kind of intuitive way, this is how you can, if you do this randomly, right? So, someone controlling your detectors doesn't know which of the states you're preparing. Sometimes they might force a detector to say 3 to click, but you send state 0, you're expecting 0 to click, you can detect that something went wrong, right? That's kind of the intuitive idea. But so, yeah, you can do this in a kind of more formal way, and you can consider the event frequencies. You can use some semi-definite programming and some take into account finite statistics, as we saw in Richard's class, and calculate or say characterize the functioning of the device through the mean entropy, which is given by the minus log of the guess probability. And so we did an experiment and showed that this device was able to produce, say, more than a bit of randomness per round, which is the best you could have with a two-dimensional system would be 1 bit of randomness. We could get a little bit above that in practice, right? Okay, so now finishing step, I just wanted to say some final remarks. So, so this is the last part of my section of the class. I just wanted to say I hope everyone heard Fernando Brandão's kind of closing remarks yesterday. They were really good. I would like to say something exactly the same. I cannot say it better than him, so here it is again. But I did want to add something, and that is that it's a really exciting time now in quantum information, and for all these reasons which Fernando said, but also for this fact that now we have these theory and proof of concept experiments, which are now becoming like real sophisticated devices, right? So, most of you, I'm assuming, program in Qiskit. So, I've been working in experimental quantum information for almost, say, 20 years. I went to program in Qiskit, and I did like teleportation or something, my first circuit, and like a tear rolled down my cheek, when I executed the program. Of course, so it's, this is really cool, right? And of course, it's important for us as quantum information scientists, because this means there's lots of new opportunities, lots of new problems appearing, because now these devices are kind of entering, say, the real world, and people are really trying to use them for something. So that's good to see that as an opportunity, and of course, good job opportunities and things like this. So. Yes, that's really cool. And that's what I just wanted to mention also, so in Concepción, we also have a spin-off company doing exactly these kind of random number generators. So this is a self-testing quantum random number generator, so it's kind of a semi-device independent device. And so, so the company started about 3 years ago with some of these founders. Many of you probably know Marcin Pawlowski and Gustavo Lima. And so we've been able to actually make a commercial device and actually sell it to some people. And it's actually, right now, the lottery in Concepción, the Kino, and some other games are using this device to draw the numbers. And so it's been like, I want to kind of share that experience with you, because it's been really fun and different and cool. The fact that, things I wrote in paper, in the introductions of the paper for 20 years now, like, are actually coming true. It's cool. Finally, just in this regard, the randomness, so we have a device that's hooked up online. So if you do, say, some sort of simulation, Monte Carlo, whatever, and you want some good randomness to do something, you get in touch with me, because I can give you access. And it's really easy. There's an API, and you can have some code in Python I can send you, and you can put this in your thing, right? The token that's here will not work. That's an old one, so don't try to just copy this. It's not going to work. Yeah, so that's it. And so sorry, Esteban, thank you for the extra time. And yeah.